Good afternoon, all of you. I'm Reena Jain from Delhi itself, and I'll be teaching you covalent bonding today. But before we start with covalent bonding, I would like to discuss what exactly is bonding and why is it formed. Now, chemical bonding, basically, it is an attractive force between the two atoms, and hence due to this force of attraction, the two atoms get bonded up in the form of bonding. Now, the next question which immediately comes into our mind is, why do atoms form bond? Why can't the atoms remain as such? And the answer is that atom bonds in order to attain the stability, and that is what the bond is formed by. Now, there are three types of bonds if we study the broad category, keeping aside hydrogen bonding and the van der Waals forces. Broadly, the bonding is categorized into three types. We have ionic, covalent and metallic bond. Ionic bond is formed by transfer of electrons. We have the cation and the anion coming together by the force of attraction, forming as ionic bond. Then covalent bonding is formed by sharing of the electron pairs. And finally, we have metallic bondings where we have positive kernels in form of the metal atoms and the electrons flowing around it, and it is what is formed by the metallic bonding. Now, when we move on to covalent bonding, as usually, we'll start from the ground level, from the scratch level. We'll develop the concept and then move on to the higher level and do the application part also. But to start with the bonding, the very first concept we should be aware of is the octet rule, the Lewis concept. Then we will move on to how to determine the shape of the molecules in terms of the Vesper theory. Then further, slightly on a higher level, we'll study what exactly do we mean by the valence bond theory, then hybridization, and finally the molecular orbital theory. But to start with, we'll start with the octet rule and the Lewis concept. Now, octet rule was introduced by Kossel and Lewis in the year 1916. And in this rule, basically it is, since we are studying covalent bonding, so we will restrict ourselves to the sharing of the electron pairs. So, this talks about that the valence electrons of the combining atom, they are shared between the atoms so as to form the bonding. This model, the Lewis concept, was later on modified by Langmuir in the year 1919, and finally it was known as the Lewis-Langmuir theory for covalent bonding. Then in the Lewis concept, the valence electrons, they are taken as dots or crosses or whatever you are comfortable with, but there should be something which can denote the valence electron, and remember, we'll restrict ourselves to the valence electron. First of all, we write down the atom, the element, the symbol of the element which we want to write. Then write down the valence electrons in the form of dots or cross, and then finally try to establish the bond. If one pair of electron is shared, single bond is formed. If two pairs of electrons are shared, double bond will be formed. And if three pairs are shared, then triple bond will be formed. And each combining atom should at least contribute one electron, because a bond is formed by two electrons, sharing of two electrons. And then the combining atom, then in what order are the atoms going to combine? There should be some rule by which we can know that how many electrons the atom is going to share. That is nothing but the octet rule that says that atom shares the electron in order to complete their octet. I hope all of you understand what do we mean by octet. 8 electrons in the valence shell. Let us see some very simple examples to start with. Cl2, chlorine is halogen, number of valence electron 7. One chlorine I have denoted 7 dots indicating 7 valence electron. And just to distinguish the electrons, I have denoted the 7 electrons of the other chlorine atom with 7 crosses. When these two atoms, they share electrons, a bond is formed where an electron pair is shared, and since only one electron pair is shared, it is a single bond that is established. Then we have another example in form of ammonia. Nitrogen atom, being the central atom, is having 5 valence electrons. So, this is what I have shown: 1, 2, 3, 4 and 5. And each hydrogen atom is having only 1 valence electron. So, what happens is one hydrogen atom with one valence electron share one electron of the nitrogen atom. This is how 3 bonds will be formed, and 2 electrons remain as such on the nitrogen atom, which we call as lone pair. So, lone pair basically they are the electron pairs which remain on the atom. Bonded pairs are the pairs like this pair as well as this pair. They are bonded pairs. Bonded pairs are the electron pair which remains in between the 2 atoms. Now, we will slightly complicate the examples. In case of chlorine and ammonia, only one electron pair was shared, and hence we say that a single bond was established. But there may be cases where 2 or 3 electron pairs can be shared. For example, in oxygen molecule, each oxygen molecule is having 6 valence electrons. So, these are the 6 valence electron on one oxygen atom. The 6 valence electron of the other oxygen atom I have denoted by cross, and when these 2 atoms share electrons, then again they are sharing 2 electrons each, that means 4 electrons in all, and hence we say that a double bond is established. Similarly, if we go to nitrogen, nitrogen atom is having 5 valence electrons. So, this is what I have drawn 5, that means it is 3 short of octet, and hence it will like to share 3 electrons with the other nitrogen atom, and this is what it is doing. It is sharing 3 electrons forming a triple bond, and the remaining 2 electron remains localized on each of the nitrogen atom. Please remember one thing, because this we are going to continue till the end, that bonded pair is under the control of 2 nuclei. Okay, bonded pair is under the control of 2 nuclei because it is present between the 2 nuclei, whereas the lone pair is under the control of only 1 nuclei. Okay, it is localized over 1 nuclei. Then let us further complicate the system. Let us now move on to heteroatomic molecules like CO2. Carbon is a tetravalent species. Carbon is tetravalent. It is having 4 valence electrons and it is 4 short of the octet. So, it would like to share 4 electrons. Oxygen is having 6 valence electrons. It is 2 short of the octet. So, oxygen will always like to share 2 electrons. So, and please remember that it would have been possible that in case of CO2, even this structure could have been possible. We could have oxygen in the center. Even this could have been possible, but whenever you will see the structure of CO2, you will always see carbon at the center, because all these are based on the experimental facts. There are various experimental techniques which establish that CO2, carbon is in the center and it is a linear molecule, and that on that basis we have written these dot concept. Obviously, we will develop it later on, then you will come to know more about it. But when we draw CO2, then we have carbon atom in the center. Each carbon atom is having 4 valence electrons, plus we have oxygen atoms surrounding it. Each oxygen atom is having 6 electrons like this. So, if this oxygen atoms share 2 electrons of carbon, its octet will be complete. Similarly, the octet of this oxygen atom is also complete and the octet of carbon is complete like this. And since carbon is sharing 2 pairs of electron with this oxygen, it is C double bond O. With the other oxygen also it is sharing 4 electrons, so C double bond O. This is the structure of carbon dioxide. Okay, then next is N2O. We are further complicating it. Listen, we started from the simplest molecule, that is Cl2. We move on to double bonded species, we moved on to triple bonded species, then we moved on to heteroatomic molecule, but a simpler molecule like CO2. Now we are further complicating it with taking further examples like N2O. Can you just write down, I am giving you 1 minute to write down the structure for N2O, the Lewis structure for N2O. Are you able to write it? I guess yes, because now you can first of all identify the atoms. We have nitrogen atom in the center, one nitrogen on the left hand side and one oxygen on the right hand side. Now start with oxygen. Oxygen is just 2 short of electrons to complete the octet. So oxygen will always prefer to form a double bond. The first preference will be double bond. Nitrogen atom, it is 3 electrons short of the octet. So nitrogen will always prefer to form 3 bonds. If it is forming 4 bond, it will be with positive charge. Look into the next element down the group, that is phosphorus. Phosphorus is having d orbital. Phosphorus is capable of forming 5 bonds, but nitrogen will never form more than 3 bonds. Okay, if it is forming, it will be with a charge. So this is what is the structure, the Lewis structure. Okay, another advantage of the Lewis structure, because as such the Lewis structure is the first ladder to study the covalent bonding. The first thing which we study is the Lewis structure, whether it is covalent bonding or ionic bonding. It is very, very important to study Lewis structure, because this Lewis structure we are going to take care of even when we do Vesper theory, even when we do hybridization. Every time we will be taking help of Lewis structure. So you should always be able to write down the Lewis structure. Another advantage of writing down the Lewis structure, you can see, are you familiar with this symbol? This is for resonance. That is, whenever you have to write down the resonating structure, what all possible resonating structures are there for a particular species, you should be able to write down the Lewis structure. So this is what the major advantage of knowing the Lewis structure, and it is very essential for you to know the Lewis structure. Then, and whenever you write the resonating structure, I hope all of you know the trick for writing down the resonating structure. It is always the movement of 2 electrons. The nuclei remain the fixed. You can't change the position of nitrogen and oxygen. You can't do that. But you can just change the position of a pair of electrons. So this is what happens here, that this negative charge moves on here, the double bond moves on here. So this will get 2 minus, oxygen will get a positive charge, or if there is the possibility of the other way round flow of electron, you will get this structure. Similarly, for ozone also we can write down the resonating structure. Each oxygen is short of 2 electrons. And it is because of this resonating structure that this ozone, because of the resonating structure, what happens is that OO bond is in between a single and a double bond. It is neither a pure double bond nor a pure single bond. It is in between the two because of the resonating structure. Okay, so Lewis structure definitely has a lot of advantages. You can write down the resonating structure. You can also get some idea about the bond length in terms of whether it is a single bond, a double bond, a triple bond, or in between the two. Like in ozone, it is in between the single and the double bond because of the resonating structure. Now we further complicate it. Okay, now before moving on to the next examples, let us now discuss the limitations of octet rule and the exceptions of octet rule. Now, if you recollect, few moments back I said that atoms combine in order to attain the octet, 8 electrons in the valence shell. But there are a number of exceptions to this. Some species have less than 8 number of electrons in their valence shell. Say for example, all the compounds which are formed by the second and the third group elements like BCl3. Boron is having 3 valence electrons. That means 1, 2, 3. And each chlorine atom is having 7 valence electron. It is only 1 short of the octet. That means it is going to share only 1 electron with the boron atom. Like this. Similarly is the case of the remaining chlorine atoms. This is what happens with chlorine. The octet of chlorine is complete, but boron is having only 6 electrons. Instead of 8, it is having only 6 electrons. That is, it is electron deficient. Same is the case with aluminium chloride. Okay. Same is the case with the other boron trihalides like BF3. If I just write down the complete series, BBr3 and Bi3. In all these series, boron atom is electron deficient. That is why they all act as Lewis acids. They all act as Lewis acids because they are electron deficient and hence they have capability to gain 2 electrons to complete their octet. Okay, so such type of compounds are on one extreme, which are electron deficient. On the other extreme, we have compounds which have more than 8 electrons. And definitely, whenever we talk about compounds which have more than 8 electrons, the central atom will be always from third period or onwards. Because second period elements, they do not have d orbitals, they cannot expand their octet. But if we have higher elements like sulfur or phosphorus, then they have a tendency to expand their octet because of the availability of d orbital. So whenever the central atom is having d orbital, there will always be a tendency to expand the octet. Say for example, SF6. I have taken the example of SF6. Sulfur atom, the number of valence electrons on sulfur atom, 6. And it is too short of the electrons to complete the octet. Each of the fluorine atom, the number of valence electron on each fluorine atom is 7. It requires only 1 electron to complete the octet. So this is what is happening here. Each fluorine atom is having 7 valence electron. It is only 1 short of the octet, and that electron it is sharing from the sulfur atom. Okay, so the octet of each of the fluorine atom is complete, but at the same time, sulfur atom is having, instead of 8, it is having how many electrons? 12 electrons. So instead of 8, it is having 12 electrons. It has expanded octet. Third category of molecules that again are exceptional are the odd electron molecule. Because if again you recollect back, we said that bonding takes place between the electrons, and as a result of bonding, there is a pairing of electron. But we do have cases where the atom is having the odd electron, and the very common case is NO2. And this is the reason which you will study later on, I think in your 12th standard, that NO2 dimerizes. It dimerizes because it is having odd electron. Anything which is having odd electron will not be special, will not be stable, and in order to stabilize, either it will lose that electron or it will form a bond with the other molecule. So NO2 dimerizes readily. This is the basic reason, because it is having the odd electron. Now let us quickly do certain problems. The first question is very simple. I'm just giving you 2 minutes to try to solve them out. In first question, you have to identify the mistake that has been done. And in the second question, you have to draw the Lewis structure. In first case, it is very, very simple. Double bond between carbon and hydrogen is not possible, because hydrogen is having one electronic configuration. It can at the most form only 1 bond, whereas in this case it is forming 2 bonds, and hence the structure is incorrect, and the correct structure will be, and where to put this double bond? between carbon and oxygen, because oxygen always prefers to form a double bond. Moreover, this oxygen is a neutral atom. Had it been minus charge, then single would have been okay, but it is a neutral atom which will always form a double bond, and hence the correct structure is H, single bond C, H, H, C, double bond O, O, H. Okay, this is the correct structure. Then we move on to the Lewis dot structures for H2SO4. At least you write down the questions quickly so that later on we can discuss all the answers together. Just write down the 4 molecules that I have given: sulfuric acid, phosphoric acid, and the other oxy acids. Are you aware of the other oxy acids of phosphorus? H3PO4. Then we have H3PO3, H3PO2. All the 3 cases. Then SO3, and finally HN3. It is not ammonia, it is HN3. Okay. Answer 1 we have already discussed. Now, the second was the structure of sulfuric acid. There are various structures which have been given in different books. Some book says it is S single bond O. Some book says it is a coordinate bond. Some book says it is a double bond. Okay, different books have given different versions. Now, a coordinate bond, whenever a coordinate bond is formed, coordinate bond means that the 2 electrons which are required for bond formation, both the electrons are coming from the same atom. The same atom is giving both the electrons which are required for bond formation. That is why it is shown with an arrow. S, arrow O, that means the electrons which are required for the bond formation, both the electrons are coming from sulfur. They are going to oxygen. Oxygen is not contributing any electron towards this bond formation. This is what we mean by coordinate bond. But once a coordinate bond is formed, it is as good as a covalent bond. Please listen to it carefully because this is a slight misconception in our mind, because we start thinking in the other direction that since both the electrons are coming from the same atom, it should be an ionic bond. But the fact is, as soon as coordinate bond is formed, it is equivalent to a covalent bond. Because if we look at the properties of such compounds, the properties reflects that such type of bonding is closer to covalent bonding. Okay, so this is a misconception, that though both the electrons are coming from the same atom, but still it is a covalent bond. And as soon as coordinate bond is formed, this can be formed. This can be written to equivalent to S single bond O. Okay, so this structure or this structure as such, they seems to be identical because the coordinate bond are being formed which are as good as a single bond. So they are identical. But what about this structure? This structure says that sulfur is forming 2 double bonds. Please note that sulfur is an element of 3rd period. It is having d orbitals. It can expand the octet also. And since it can expand the octet, it is capable of forming more than 2 bonds. It is capable of forming more number of bonds, and that is what it is doing. If you write down the Lewis structure of sulfur, the electronic configuration says that it is having how many valence electrons? 6 valence electrons, like this. Okay. Then we have oxygen. Now again the question arises, why can't we have hydrogen directly bonded to sulfur? Why do we have hydrogen bonded to through oxygen to sulfur? This again is a question. But the fact says that sulfuric acid is an acid. It is an acid, so for acid to be formed, it has to be a OH bonded to the central atom. H will not be directly bonded to the central atom for acid species. Okay, it has to be through oxygen, so that on ionization this hydrogen breaks up, imparting acidic character to the species, leaving only the anion. Okay. So, definitely this is a major disadvantage of inorganic chemistry, that we can say that at times most of the explanations which we give are based on the experimental facts. Okay. Now, this oxygen atom, it is having 6 valence electrons like this. The other oxygen atom is also having 6 valence electrons like this. Then we have rest of the oxygen atoms also having valence electrons 6. Then we have hydrogen also having 1 valence electron. So, if you look at it, the octet of all the atoms are completed except sulfur, hydrogen sharing 1 pair, this hydrogen also sharing 1 pair, oxygen sharing 1 electron with sulfur, 1 with hydrogen, this oxygen again sharing 1 electron with sulfur, 1 with hydrogen. This oxygen, it is too short of the octet, and as just we discussed that oxygen will basically form a double bond, and since there are 2 electrons that are available on sulfur, so this will be the completing the octet like this, and this oxygen also will be completing the octet like this, and hence it will be HOS double bond O, double bond O, single bond OH. But in this process, sulfur is having 2, 3, 4, 5, 6, 7, 8, 10 electrons. It is having an expanded octet, and it can afford to do that because sulfur is having d orbitals in it. Then another example I gave you of the oxy acids of all the phosphorus. We have H3PO4, H3PO3 and H3PO2. Again, there are different versions which have been given in different books. We have single bond, we have coordinate bonds also, and then we have double bonds also. And again, phosphorus belongs to third period. It is having d orbitals available. It can expand the octet. Now, phosphoric acid is a slightly different case in comparison to sulfuric acid and nitric acid. And to study this series, one should always start with H3PO4. Now, it has been an established fact that H3PO4, it is a triabasic acid. Now, if it is a triabasic acid, it should have 3 OH bonds. That means we have phosphorus, 3 OH bonds like this. And then we have double bond O. Okay. Now, again in this process, you can see the octet of phosphorus is expanded. It is having 10 electrons around it, and it can afford that because of the presence of d orbital. So, it is a triabasic acid. Then we move down to lower oxy acid, which is H3PO3. Now, it appears that H3PO3 again should be tribasic. It should have 3 OH. From the formula, it appears like this, but actually it is not. This again is a very, very important question, maybe at the 12th class and definitely at the high level, because by the formula it appears that phosphorus acid is a triabasic acid, but it is not. It is a diabasic acid. That means how many OH groups? It should have only 2 OH groups. 2 OH groups, 1 direct H and 1 double bond O. Okay. Then we move on to the other oxo acid, which is phosphonic acid, H3PO2. So, we have a triabasic acid, a diabasic acid, and H3PO2 will be a monobasic acid, and hence only 1 OH group. 1 OH group, we are left with 2 more hydrogen atoms and 1 oxygen atom. We cannot have OH group, more OH group. So, 1 double bond O, 1 H, another H like this. And please keep this, all the 3 oxo acids of phosphorus in your mind, because later on when we are going to discuss hybridization, then also we will take this example. We'll discuss the hybridization of phosphorus there also. So we'll correlate it with this. Okay. Now, another application of Lewis acid concept. One we have already done. It helps us in writing down the resonating structure. The second also we have done. On the basis of resonating structures that can be written, we can find out the bond length, whether it is a perfect bond length or it is in fraction. Another very important example is with the help of the oxo acids of phosphorus. This is a tribasic acid, diabasic acid, a monobasic acid. Okay. Now, on the basis of the number of hydrogen atoms directly attached to the cell atom, we can also comment on the reducing nature. So, this is another application of the Lewis concept, the reducing nature. More is the number of hydrogen atoms directly bonded to the central atom, more is the reducing power. So, out of the three, which one should be the strongest reducing agent? H3PO2 should be the strongest reducing agent. Now, whenever we talk of reduction, we can always talk of oxidation in parallel. So, another application is in the form of oxidizing agent. Since H3PO2 is the strongest reducing agent, it is going to be the weakest oxidizing agent, and hence H3PO4 is the strongest oxidizing. The species which is having least number of hydrogen atom directly bonded to the central atom is weakest reducing agent, strongest oxidizing agent. Okay, so this again is a very important application of the Lewis concept. The third molecule which I gave you is sulfur trioxide, SO3. Again, there is a variation. I have given only this structure, but actually, according to this structure, if we have this as the correct structure, where we are having a double bond and a coordinate bond, the bond length, SO bond length, should be in between a single bond and a double bond. Because of the resonating structure, as we have already discussed, or we can write down a single bond, OO. And since there are all sort of resonating structure, double bond in one structure, it can be here, double bond oxygen can be at this position as well as on this position. So, double bond is rotating around the molecule. That means throughout the molecule, we can have all the three structures, they are equivalent to this structure, which indicates that each of SO bond is in between a single and a double bond. But experiment says that all the three SO bonds are equivalent and they are equal to S double bond O. All the SO bonds are equivalent and not in between a single and a double bond, but perfect double bonds. That means again, because sulfur is having the d orbitals available with it, it can expand its octet, and hence the Lewis structure actually is this. Okay, this is the actual Lewis structure for SO3. We'll again get back to this when we discuss the hybridization, the type of hybridization the sulfur atom is going. Next example which we have discussed was HN3. Again, you can just quickly see the structure. Again, we have written the resonating structure, which indicates that this is helpful in resonating structure. Like in most of the MCQs that you get, it may be given as a choice or in the form of the resonating structure, or they may give you a simple structure and ask you whether it is a correct structure or predict the correct Lewis structure for HNO3, something like that. Okay, then you need to know how to write down the Lewis structure. Another question is this, that in the dot formula, the carbon dioxide, in both the structure, whether it is this or this, the octet is satisfied. But which is the correct structure? A, because there is no charge. B's choice says A is better because all bonds and non-bonding electron pairs are arranged in symmetrical manner. C says that B is better because there are opposite formal charges, and then D say that B is again better because the bond energy of single and a triple bond is higher than that of a double bond. What do you think is the correct answer? A. A or B? Listen, in a molecule you can have a formal charge. If you just look at this example, HN3, we do have charges in between. We do have a positive charge, we do have a negative charge here. But look at the molecule as a whole. This positive charge is getting neutralized by the negative charge, and as such, the whole molecule is a neutral entity. Okay, as such, the molecule is a neutral entity here. So definitely in this case, since both the electrons are arranged in a symmetrical manner, so structure A is correct. That is, the correct choice is B and not A. Okay? We have more questions in store for you people. For water, we all are aware water is a simple molecule that you can write down the electronic dot structure. Which structure do you think is the correct structure for water? A? Because in this case, hydrogen cannot have so many electrons. This is ruled out. In this case, oxygen cannot form 3 bonds without a charge. So this again is ruled out. In this case, oxygen is not having sufficient number of electrons. It is just having 1, 2, 3, 4, 2 electrons short, 2 lone pairs. And oxygen is having 2 lone pairs, and it is showing only 1 lone pair. So the correct structure is A. Then next question we have for hydrogen cyanide. Can you just quickly try for hydrogen cyanide? HCN. H, single bond C, triple bond N. So how many single bonds you have? You have CH single bond. You have one CN single bond. You have one C pi bond here, the other pi bond, that is, this is a sigma bond, this is a pi bond, the other one is also a pi bond. And what about the lone pairs? Is this structure okay? Is this structure okay? In this structure, there should be one lone pair on nitrogen also. And hence, on the basis of information, which should be the correct choice? Which should be the correct choice? E, triple bond between C and N, one CH bond and one lone pair on nitrogen atom. So the correct answer is the last choice, that is E. We have next question. The correct dot formulation for NCl3, nitrogen trichloride. Please remember, count the number of total valence electron carefully, because the choices says that along with the normal bonds, you should be able to know the number of lone pair of electrons also. So NCl3, nitrogen is having 5 valence electrons like this. It is forming bond with 3 Cl atoms. Each Cl atom is having 7 electrons. This is how we can write the electrons. I am just writing them with crosses in order to differentiate between the two types of electrons. So the bond is established like this. And hence, when you rewrite in terms of lone pair, we have nitrogen atom with 1 lone pair, single bond C, single bond Cl, single bond Cl, and each chlorine atom having 3 lone pairs. 1, 2, 3. 1, 2, 3. 1, 2, 3. Means 3 plus 3 plus 3. 9 plus 1 on nitrogen. 10 lone pairs plus 3 N single bond Cl. And hence the correct here is A. Okay? Next. Okay. This is an interesting one. Which of the following violates the octet rule? The first example is PCl3. PCl3 is perfectly okay, Then we have Cbr3, it is again okay. Carbon is tetravalent, here it is forming only 4 bonds, it's perfectly okay. NF3 again is perfectly okay. OF2 is parallel to water, again is perfectly okay. So automatically AsF5 is odd man out also in this question. So in some of the questions, you can predict the correct answer by the way of elimination also. Moreover, arsenic is having 5 valence electron. If you count the number of electrons, 5 valence electrons on arsenic plus the fluorine atom. So definitely when 5 valence electron of arsenic, it is sharing 1 electron with each of the fluorine atom. The total number of electron on arsenic becomes 10. It is more than 8, and hence the correct choice is E. Then we have question number 8, where we have to predict the correct structure for PBr3. Can you just quickly tell me? PBr3. Phosphorus is in the same family, nitrogen family. It is having 5 valence electrons. It is forming 3 single bonds with bromine plus 1 lone pair. Isn't it? So the correct choice should be C. Moreover, halogens will never form double bond. They are 1 electron short of the octet. So this choice is ruled out. This choice again is ruled out. In this choice, what is the problem in this choice and this choice now? Correct choice ideally is either this or this. But the actual answer is A, because in this case it is also showing the lone pair on bromine. It is showing the lone pair on bromine as well as on phosphorus. This is also correct. It is showing the lone pair only on phosphorus. Sometimes we may have situations where 2 answers seems to be correct, as in this case. In that case, you have to use your brains and see which out of the 2 is better. This is okay, but this is slightly better because it is telling us the number of lone pair on the bromine also. And in the previous case, we have already done an example where counting the total number of lone pairs. Just now we did that example in Cl3, I guess. We were asked to count the total number of lone pairs. So out of the 3 choices, A is better. Okay. Then, which of the following is not a valid Lewis structure? This again should be very quick. D. Oxygen forming 3 bonds. Oxygen doesn't have d orbitals. It requires only 2 electrons to complete its octets. It cannot form free bonds. So this is the correct answer. Then we have CH3Cl, chloromethane. Which should be the correct choice? Quick. Remember, whenever we have carbon, it should have 4 bonds. B is the correct answer. Very good. Because in this case, it is forming 3 plus 3, 6 bond. Not possible. For chlorine also, it is forming 3 bonds, which again is not possible. Okay. In this case, again Cl is in the center. So that means it is forming 6 bonds. Not possible. In this case, Cl again forming double bond. Again not possible. So the best choice is B, which is the correct choice. Then this is a very simple one. A set a question for N2 molecule. This we have already done. For N2 molecule, we all know that it is N triple bond N. N triple bond N, obviously this choice is ruled out. Apart from a triple bond, nitrogen is also having a lone pair because each nitrogen is having 5 valence electrons. 3 are involved in bond formation, 2 electrons remaining as the lone pair. So the choice is A. Okay, then we have question number 12. This we have already done. I've given you the same series of oxo acids. You have to comment on their acid reducing and oxidizing character. Reducing character, we have just discussed which one is the best reducing agent. H3PO2. The best oxidizing agent, H3PO4. And the strongest acid, H3. There's a slight debate on the strong acid. Some book says it is phosphoric acid. Some book says it is phosphorus acid. Actually, it is phosphorus acid, H3PO3. Okay? This is an exception. That is why I have discussed it. This is an exception. Normally, when you do a series out of sulfuric and sulfuric acid, sulfurous and sulfuric, we say sulfuric is a stronger acid. Out of nitrous and nitric acid, we say nitric acid is a stronger acid. But out of phosphorus and phosphoric acid, phosphorus is a slightly stronger acid. There is a slight difference in acidity. Okay. And finally, though we have discussed there are a lot of advantages of using the Lewis concept. We are able to write down the resonating structure. We are able to comment on the acidity as well as the reducing and the oxidizing agents of a particular species. But there are still a few drawbacks on the Lewis structure. And the major drawback is that it is not able to give us any idea about the shape or geometry of a molecule. This is the major limitation. Another problem is that the Lewis theory is not able to tell us about the magnetic behavior of a molecule. Say for example, we have already done oxygen molecule. Oxygen molecule, we have shown that it is formed by sharing of two pairs of electrons like this. These are the two oxygen atoms. Each oxygen atom sharing two electrons, and hence a double bond is established. Plus, there are two lone pairs on each oxygen atom. Now, oxygen atom, if it is having lone pairs, that means the electrons are paired up. That means it should be a diamagnetic molecule. Whenever the electrons occur in pair, it gives a diamagnetic character. Whenever we have unpaired electrons, it becomes magnetic. So, according to the Lewis structure, oxygen molecule should be diamagnetic. But actually it is paramagnetic. So again, this is a major limitation of the octet rule, and hence we require to study more theories to have more clarity, to have a broader picture of what exactly the covalent bonding is. And hence, in order to explain the structure, the shape, the geometry, we say we have to have another theory which is better than Lewis theory, and that theory is nothing but the Vesper theory, VSEPR theory. The Vesper theory is the valence shell electron pair repulsion theory. Now, if you look at the Vesper theory basically is that the Vesper theory remains the same, that you write down the Lewis structure first. The first requirement is that you need to write down the Lewis dot structure. That is why I said that Lewis structure, though it is the first ladder to know the covalent bonding, but you can't climb unless and until you step on the ladder. So the Lewis concept will always be useful. We have to always use Lewis concept even for higher models that we study in the covalent bonding. Okay. So in Vesper theory, first of all, we write down the Lewis concept, the Lewis structure of a particular molecule, and then after writing down the Lewis structure, say for example in CO2, according to the Lewis structure, both the structures which I have given, A and B, should be correct, because in both the case the octet of all the three atoms is complete, whether I write down the atoms in a straight line like this, or I bend them, that is like this. Whether I write them in the straight line or at an angle of 70 degree or 80 degree or 40 degree, the octet is complete. It should be immaterial for me. But actually these two structures, they differ. If I'm writing this structure, I'm saying that the molecule is a linear molecule and the bond angle is 180 degree. But if I'm showing it as a bent structure, I mean to say that OCO bond, this angle should be something less than 90 degree or 90 degree. But at the same time, I need to define that bond angle. And in order to define that bond angle, we look at the Vesper theory. Vesper, as I have said, you need to write down the Lewis structure, the dot structure. We place the electrons from each other in order to minimize. The shape of the molecule is based on the minimum repulsive interactions. Basis should be that after write down the Lewis structure, we should try to have the electron pairs as far as possible so as to have the minimum repulsions. So the Vesper theory was initially I think we can skip this so as to have a minimum repulsion. Say for example, if we are having two bonded pairs, two electron pairs, they can be put together to have a minimum repulsion at a bond angle of 180. We have three bonded pairs. Then in order to have minimum repulsions, the bond pair should be at an angle of 120 degree. This is what is happening in this case. If we have three bonded pairs, four bonded pairs, then in order to have minimum repulsion, they should be in a tetrahedral order, that is 109.5 degree. There is another possibility if we are having four atoms surrounding the central atom. Suppose this is carbon. We are having four atoms surrounding this carbon atom. Okay, and we say that it is a tetrahedral arrangement, 109.5 degree. Obviously, you'll have to visualize how a tetrahedral look like. It is not a two-dimension thing, so it is not easy to visualize. You just have to think how a tetrahedral look like. Okay, and the bond angle is 109.5 degree. There is another, when we are having four atoms surrounded this atom, there is another possibility. Atom should be placed along the corner of a square, giving it a square. Now, according to the Vesper theory, we are basically encashing on having the minimum repulsions, and hence we, in both the cases out of the two, which one is the best option? This is the better option, where the bonded pairs are much away from each other at an angle of 109.5 degree in comparison to the square planar structure. So whenever we write a molecule which is having four bonded pairs, our preferred geometry is tetrahedra so as to have minimum repulsion. But that doesn't mean that the square planar geometry is ruled out. We do have examples where there is a case of square planar geometry also, that we'll discuss later on when we talk about hybridization. Now, if we have five pairs, again a typical case where it is a trigonal bipyramidal type of geometry. Say for example, this is the central atom. We have three bonds like this, 1, 2, 3, one above the plane like this and one like this. So five bonds in all, and geometry is a trigonal pyramidal geometry, which we call TB type of a geometry. That is trigonal bipyramidal type of geometry. This is a very special type of geometry because in this geometry, what happens is that we have these three bonds. These three bonds are as good as a triangle, and so this bond angle between these three bonds, this bond angle as well as this bond angle, each bond angle is 120 degree. Whereas these two bonds, they one above, one below the central atom, they are at an angle of 180 degree with each other, with respect to each other, I mean to say. And these three bonds which are forming a triangle, they are known as equatorial bond, and these two bonds are known as axial bond. Please, this is a very important point because later on hybridization, then again we'll take point when we talk about certain examples that we'll discuss, we'll again take care of this point. So this is really very, very important. So please hear it carefully. Diagonal middle type of a geometry, there are two types of bonds. Bonds are at an angle of 120 degree to each other. Axial bonds are at an angle of 180 degree to each other. But the bond angle between axial and equatorial, this bond angle is 90 degree. आगे करिए, next. Okay, so this bond angle is 90 degrees. So this is a very typical case. Moreover, since we have equatorial bonds, we have axial bonds. Axial bonds are longer than equatorial bonds. Okay, they are always longer and hence weaker than equatorial bond. So please note all these points very carefully, because later on when we talk about hybridization, we'll refer back to all these points, and most of the applications related to such type of molecules will be based on the structure only. Okay. So again, I think we can move ahead. Now, initially this type of a bonding, but later on when the Vesper theory was modified, Nyholm and Cbse, they introduced the concept of and the bonded pair, that the lone pair, bonded pair is under the control of two nuclei. Lone pair is under the control of only one nuclei. So out of the bonded and the lone pair will expand more. It will try to occupy more space. So since lone pair occupy more space, so lone pair will be very strong, followed by lone pair bonded pair, followed by bonded pair bonded pair. Okay, just because of the fact that lone pair is under the control of only one nuclei, it will occupy a lot of space. Okay, now this is a very important point which we should always remember, that a covalent molecule, it will have a regular shape or a geometry only when it is surrounded by all the bonded electron pair with similar atom. Say for example, we have talked about a case where the coordination number was 4 and the geometry was the tetrahedral geometry, the true geometry that we have just discussed out of different tetrahedral. We have a molecule like HCCl4 and CHCl3, carbon tetrachloride and chloroform if we are comparing. Okay, in both the cases, it is a tetrahedral geometry. In one case, all the 4 atoms which are bonded to the central atom are exactly the same. In the other case, there are 3 atoms which are of one category. There is one different atom. There are maybe two varieties or 3 varieties of atom that can be attached to the central atom. Then what happens is as a normal person, it appears that in both the cases, it is a tetrahedral geometry. Bond angle should be 109 degree and a half degree. The bond lengths also should be equal. But actually what happens is, this is symmetrical molecule where we are having all the surrounded atom of the same type. But this molecule, there is a slight distortion in geometry, isn't it? Because we are having 2 varieties of atom. They differ in electron. Normally when we write down in answers, we call this as tetrahedral as well as this as tetrahedral. We do not consider that distortion to be a major distortion, but there is some distortion. So this is what point number 1 says, that a covalent molecule, it has a regular geometry if the central atom is surrounded by all bonded electron pairs with the same atom. Then only it will have a perfect geometry. There will be some distortions in the geometry if the atom changes. Okay, but that distortion is not a major distortion. So generally we neglect such type of small distortions. But instead of bonded pair, if we have lone pair, then it will be a major distortion in geometry. Say for example, if instead of this example, I move on to ammonia. In case of ammonia, the geometry is tetrahedral. Have 4 pairs. Geometry is tetrahedral. The difference between geometry and a shape. Okay, is what actually is the shape of molecule, taking into the consideration the effect of the load also. Geometry, both the molecules have the same tetrahedral. Even this is tetrahedral geometry, but the major and one lone pair. Lone pair occupies more space, more repulsion, and hence these three angles will compress less than 109.5 degree. This occupies more space, and due to this distortion which is caused by the lone pair, the shape changes. It is no longer tetrahedral. It becomes pyramidal. Next. आगे बढ़ा दीजिए. Okay. So this is what I have written here is that if you have 2 pairs, both of them obviously will be bonded. If you have one bonded pair, one lone pair in case of cyanide, then it's of not much of use. If you have 2 pairs, it has to be linear. If you have 3 pairs of electron, then there are possibility if all the 3 electron pairs are bonded, then it is a perfect geometry, but that is trigonal planar. But if out of 3, 1 is lone pair and 2 are bonded, we will not call the shape to be trigonal planar, we will call it bent shape. Next is we are having the 4 number. Again, there are various 4 bonded pairs, just like in CCl4 or CH4 tetrahedral. If instead of 4 bonded pair, we have 3 bonded pair and 1 lone pair, just like in ammonia, it will be a trigonal pyramidal geometry. Then 2 bonded pairs, lone pairs. Then, like in cases for coordination number 5, this is just a pictorial representation of what I talked about, trigonal bipyramidal type of geometry. We have 2 types of bond, equatorial bonds, 1, 2, 3, and we have axial bonds. Equatorial bonds at an angle of 120 degree to each other, axial bonds at an angle of 180 degree to each other, and bond between equatorial and axial is 90 degree. Then there are certain more things which you should always keep in mind whenever you are dealing with molecules with 5 coordination number. First is the lone pair and the double bond oxygen. They will always occupy the equatorial position. If in such a geometry you have a case where you have a lone pair or a double bond oxygen, they'll either occupy either of these 3 positions. 1, 2, 3, equatorial position always. But if you have a more electronegative atom, then the more electronegative atom will always occupy the axial position. Now, a question may arise that also is electronegative. It is just occupying the axial position. Oxygen is occupying the equatorial position because it is not a simple oxygen. Oxygen always prefer to form a double bond. Double bond require more space, and a bond can get more space only when it is in the equatorial position. Hence, double bond oxygen as well as lone pair, they require more space. They will always occupy equatorial position. More electronegative substituent will always occupy the axial position, because later on when we do examples, there are examples in which you have to place the lone pairs, more electronegative atoms accordingly. At that point of time, you have to keep this point in your mind. So, if we have various combinations, first case where all the bonded pairs like this, second case where we have 4 bonded pair, 1 lone pair. As I just said, the lone pair always occupy the equatorial position. So, there where is the position of the lone pair, and hence it gives a seesaw shape. In that case, both the lone pair occupying the equatorial position, giving it a T shape. Then if we have 2 bonded pair and 3 lone pair, all the 3 lone pair occupying the equatorial position, and the remaining 2 axial will be the bonded positions, and hence it gives you a linear shape. Okay. Then 6th coordination number, it is octahedral. If we have all these 6 bonded pairs, it is octahedral. If we have 6 bonded and 1 lone pair, then out of these positions, these 4, they are in plane. So the lone pair will definitely not like to intrude at these angles. But moreover, here it will get a bond angle of only 90 degrees. So it will try to go into a place where it can expand more, and hence either this position or this position. Okay, so if you have 1 lone pair, this position, giving you a square pyramidal geometry. If you have 2 lone pair, then it will go in the top position, giving it a square geometry. So the position of the lone pair should be clearly in mind. So this again already okay. Now there are certain tips which are important. If you have only sigma bonds, this rule is valid only if you have sigma bond in your molecule. No oxygen should be there, because whenever you have oxygen, since oxygen prefer to form double bond, you cannot apply this rule. What you do is you just identify the central atom, count the number of valence electrons on the central atom, add 1 for each of the surrounding atoms, add 1 for each negative charge, subtract 1 for each positive charge, add the entire number up, divided by 2, you get the number of electron pairs, and then you divide between the bonded pair and the lone pair accordingly. So I'll show you an example for this also. Next, CH4. Carbon is the central atom having 4 valence electron, 4 surrounding hydrogen atoms. I said 1 for each, divided by 2, you get 4 pairs, and since all the 4 are bonded pairs, so we have 4 bonded pair, giving it a perfect tetrahedral geometry. Then we have another example of ammonia. Central atom is nitrogen, valence electron on nitrogen is 5, 1 for each of the surrounding hydrogen atoms, that is 3, no positive charge, no negative charge, 5 plus 3, 8, divided by 2, you have 4 pairs of electrons. Out of these 4, you have only 3 bonded pair, and the remaining pair will form a lone pair. And since you have total number of pairs, 4 pair means the total number of pairs here that you will get, that will include the bond pair as well as lone pair, will give you the geometry. The total number of electron pairs, that is the number of bond pair plus the number of lone pair, will tell you the geometry. And if you look at the effect of the lone pair on that geometry, you get the shape. Just as we have discussed, in case of C4 it is tetrahedral, in case of ammonia the tetrahedral shape is pyramidal. Okay, then this is the rule, but most of the time, in some cases also, this rule gets violated. So please do not rely much on this rule. There are cases where the rule gets violated also. This is a very rough and raw rule, I can say. Whenever you have oxygen in your compound, in that case you count the number of valence electron for all the atoms except oxygen. If the number comes out to be more than 8, you divide it by 8, and the remainder, whatever you get, you divide it by 2 further to get the lone pairs. And if it is less than 8, you just divide it by 2. I'll show you an example. Say for example in SO3, the number of valence electron on sulfur is 6. I said that if oxygen is there, you don't have to add anything for oxygen. 6, since it is less than 8, divided by 3, you get 3 as an answer. That means there are 3 bonded pairs. But please remember that whatever bonded pairs you are getting by this calculation, it is only the sigma bond. It is not the pi bond. SO3, there are 3 sigma bonds. As we have already discussed, it is like this. Okay, so pi bonds, we don't get any information about the pi bond from this calculation, only the sigma bond. Then H2SO4, 6 electrons of sulfur plus 2 for hydrogen. Since you are having a 4 of oxygen, if you are adding oxygen also, in that case again you will get, if in case you add oxygen, then 6 valence electron for each oxygen, total comes out to be 32. Then divided by 8, you get 4. In H2SO4 again we have discussed there are 4 sigma bonds between the sulfur atom. Next, okay. Let us now move on to the problems for the Vesper theory. The first question says that water molecule is triatomic but linear, but not linear. Why? Water molecule is a bent molecule. It is not linear. It could have been like this. But it is not like this. It is a bent molecule. Why? Because of the lone pair. Because this lone pair repulsion is high, it makes this bond to be bent, and hence it is not linear but a bent molecule. Then CH4 is tetrahedral, not square planar. This we have already discussed. It is tetrahedral because to have minimum repulsions, bond angle 109.5 degree. Had it been square, the bond angle would have been 90 degree, and hence repulsions would have been high. Then shape of SF4 molecule. Yes. Try it out. Since it is not having any oxygen, so it should be very simple. The tips that I have given you for SF4 molecule, number of valence electron on sulfur, 6. 6 plus 1 each of the surrounding atom, 4. That means 10 electron. That means 5 electron pair. 5 electron pair immediately gives you trigonal bipyramidal geometry. Now, since you have 5 electron pairs, out of these 5, you have only 4 bonded pairs and 1 lone pair. And as per our discussion, that lone pair will occupy equatorial position, giving it a seesaw type of a shape. Okay. Next is an interesting one, PCl4F molecule. What should be the geometry? 5 plus 4 plus 1. That means 10 electrons. That means 5 pairs. 5 pairs, that means all the 5 pair are bonded pair because it is PCl4F molecule. All 5 are bonded now. That means the geometry is trigonal pyramidal. The shape is also trigonal bipyramidal. But here you have to look at the choice of fluorine atom. Fluorine is more electronegative than chlorine. So fluorine will occupy the axial position. That means it is like this. We have fluorine. Okay. If you write fluorine here, you will not get any marks. So please be careful. The position should be very, very carefully done. This is what we have discussed back. Next, that you have the, sorry, piche wala slide. Next question is that I've given you certain molecules. You can just note them out. There are some ions also. You can just work out their geometry. And maybe tomorrow we can get back to these geometries. Will you be able to do it by tomorrow? So I think tomorrow, before moving on to the next topic, we'll get back to all these molecules that I have written. Just note them out quickly. Okay, this is a very interesting example. Again, very, very important example. NO2 plus, NO2 and NO2 minus. Okay, in first species NO2 plus, it is a linear molecule. NO2, as we have also discussed when we were talking about the exceptions of octet rule, we said NO2 is an odd electron species. It is having an odd electron on nitrogen atom, 1 electron. Then NO2 minus, instead of 1 electron, it will have 2 electrons, that is a lone pair. Now, the first case, that is NO2 plus, it is a perfect linear molecule. Bond angle is 180 degree. Okay, that is a linear molecule. NO2, it is having 2 sigma bonds and pi bonds also, but at the same point of time, because of this electron, it is not a linear molecule, it gets bent. Now, if you compare these 2 molecules, So these two species, this is NO2 and this is NO2 minus. If you compare these two species, you can see there is one electron in this species, there is an electron pair. And compare it with the bond angle, which is 132 degree and 115 degree with this here. That means this electron pair is able to expand more and hence is able to compress the bonded pairs to a greater extent. But a single electron is not able to compress the bonded pair to a greater extent. The bond angle is 135 in comparison to 115 here. That means a single electron, obviously single electron will have less effect than a pair of electron. Okay, pair of electron was carrying out more repulsion. Such type of questions normally you are asked to arrange them in increasing bond order or bond angles. So this is 180 degree, this is 135 degree, this is 115 degree. Later on we can again discuss these examples when we talk about hybridization. Next, this is a brief glimpse of what we have already done. The linear geometry, the bench, if we are having two like this, trigonal planar, trigonal pyramidal in case of NF4, T-shaped, square planar, trigonal pyramidal, octahedral, all these shapes we have already discussed. Okay, till now all these species that we have discussed, ammonia, say for example, another example, water. In case of ammonia, we said that it is having a tetrahedral geometry but a pyramidal shape. In case of water, we said tetrahedral geometry but a bench shape, because if the number of electrons on water molecule or on ammonia, I think we have already done 5 plus 3, 8 divided by 2, 4 pairs. Out of the 4 pairs, 3 are bonded, is a lone pair, and hence it is slightly distorting the molecule, giving it a pyramidal shape. Now, since in this example, this lone pair is responsible for changing the shape from tetrahedral to pyramidal, we call this lone pair to be active. This is an active lone pair. Whereas there may be cases where the lone pair as such is present but is not distorting the shape of the molecule. That means lone pair is defunct, it is inactive. That is what we call as stereochemically inactive lone pairs. Normally, all the examples that we have done till now, in all the cases the lone pair has been active. But there are exceptions where the lone pair is inactive. Now, the $1,000,000 question that arises is, how would you know that whether the lone pair should be active or inactive? Suppose you come across with an example where the central atom is on the extreme right side of the periodic table. That means we are talking about heavy elements on the right hand side, plus the coordination number is more than 6. In that case, only the lone pair may be inactive. Okay, it should be firstly the central should be on the right hand side. So all the elements that we have discussed till now, the central element has been carbon, nitrogen or oxygen. All of them were in the middle of the table, not on the extreme right. Secondly, the coordination number should be more than 6. Then there are possibilities of lone pair to be inactive. In that case again, the lone pair is inactive only if it is surrounded by larger atoms like chloride, bromide, etc. If it is surrounded by smaller atoms like oxygen or fluorine, the lone pair will be active. Okay, I'll give you an example. Technetium and antimony compounds, they are all on the right hand side, and we have bromide and chloride as the surrounding atom, larger one. Now, if you count on the basis of the tips that I have given to you, the number of bonded pairs the number of electron pairs in each of these species. Can you do that? For example, for SbBr6 minus, do you know which group antimony is in? Which group antimony is in? Nitrogen family. Okay, just calculate the number of electrons we are getting for SbBr6 2 minus. 14 electrons. That means it is having 14 total electrons divided by 2, 7 pair. Out of the 7 pair, 6 are bonded, 1 is lone pair. Okay, but since in this case the central atom is a heavy atom belonging to the right hand side, firstly. Secondly, the surrounding atom is a larger atom, the bromide ion, and hence the lone pair will be inactive. That is, it will not contribute anything towards the shape or geometry of the molecule, and hence the shape is a perfect octahedral shape. There will be no effect of lone pair. Such cases are known as stereochemically inactive lone pairs. Okay. Now, Vesper theory to some extent is able to tell us about the shape of the molecule, but still we are not very clear about the shape of the molecule because of the dicey role which is being played by the lone pair, and hence there is a scope of further modification. Now, what we do is, instead of just normally modifying the Vesper theory, we give it a flavor of quantum mechanics. You are all familiar with the atomic structure, must be familiar with the Schrödinger wave equation in atomic structure. That was nothing but the quantum mechanical treatment. So, here we will take help of the quantum mechanics and slightly try to modify the Vesper theory. Now, when we talk about quantum mechanics, there are broadly two theories which can be discussed, the valence bond theory and the molecular orbital theory. The two theories can be discussed under quantum mechanical approach, and we'll discuss both the theories. In valence bond, we'll discuss the two further theories, Hitler-London, Pauling-Slater, and molecular orbital theory was the same theory which was given by Hunz and Mulliken. So, the valence bond theory, we can call it as the first quantum mechanical approach. Okay, it was the first quantum mechanical approach that was given. That means the Lewis structures, they were expressed in terms of the wave functions. That is what is the role of the quantum mechanics, that each electron is expressed as a wave function. So, this is what we are doing here also. Now, and the basis of this molecule is that we talk about the molecular shapes with the help of sigma and pi bonds. Next. The first theory which was proposed, as I have just shown you, is the Hitler-London theory, which was introduced in 1927. According to this theory, it first dealt with hydrogen molecule, how H2 molecule is formed from two hydrogen atoms, and it says that as the hydrogen atom approaches each other, there will be some interaction between the two hydrogen atoms, and this is what Hitler-London has studied, these interactions. Now, in the first, suppose there are two hydrogen atoms, HA and HB. I am calling the nuclei of HA by Na, electron of HA by Ea, the nuclei of the other hydrogen atom by Nb, and the electron of another hydrogen atom by Eb. Now, when these two hydrogen atom approaches each other, there will be various forces of attraction as well as repulsion. Attraction will mainly be between the nuclei and the electron, between these two, as well as between NaEb and NbEa. Repulsion will be between the nuclei NaNb and EaEb. So, all such forces will be operative, and initially when these two atoms, they approach each other initially, they will be coming towards each other by the force of attraction. That means initially the attractive forces will dominate the repulsive forces, and when the force of attraction is dominating the repulsive forces, it will lead to stability. And this is what is happening. If you have potential energy versus the distance graph, this is the 0, this is the plus potential energy, this is the minus potential energy. When a system is getting stabilized, the energy will decrease, and this is what is happening here. If these two atoms further come closer to each other, then there will be further dip. This distance you can see is decreasing. Then if they further come closer to each other, this distance has further decreased. But there will be a situation where if the two atoms come further closer to each other, instead of attraction, they will start repelling. And at that point, when the repulsion begins, and when the repulsion becomes more dominating than attraction, what will happen? What will happen? The potential energy will start increasing. So this is what is happening here, that at this point where the internuclear distance, this distance is 74 picometer, till that distance the two hydrogen atoms are okay with each other, they undergo, they experience force of attraction. But if we try to move them closer than 74 picometer, then instead of attracting each other, they will start repelling each other, and then there will be an increase in the potential energy graph that I will show you. But at the same point, I would also highlight one more point here, that at this distance of 74 picometer, which we call it at an equilibrium distance, the bond energy is minus 436 kilojoules per mole. What do we mean by this minus 436 kilojoules per mole? It means that when a bond is formed between two hydrogen atoms, then 436 kilojoules per mole of energy is released. Okay, next. आगे बढ़ाइए. Okay, so this is what is happening here. Two atoms away from each other, coming closer, attracting each other, further closer, reaching an equilibrium position where the repulsive forces start dominating, and then if you further decrease it down, there will be an increase in the potential energy. So this is nothing but the potential energy versus the inter graph for hydrogen atom. And this is what happens is that there are two hydrogen atoms, and when the two hydrogen atoms bond together, the electrons should be of opposite spin. Then only they will be able to establish a bond. Next. So this is another way of representing the two hydrogen atoms. These are two hydrogen atoms, their nuclei initially they are away from each other. As they come closer, the electronic cloud between the two hydrogen atoms is increasing. Further you can see they are coming together, and here the hydrogen molecule is being formed. This is a distance of 74 picometer. Okay. Now Hitler in London, he was able to explain the overlap of two hydrogen atoms. He was also able to explain how a bond was established between the two hydrogen atoms, but he was not able to explain the shape of the molecule. Still, that's the mystery. To explain the shape of the molecule, the work was mainly done by Pauling. This is what I initially showed you, that there are two ways of explaining the valence bond theory. One is the Hitler-London, other is the Pauling. So Pauling basically concentrated on explaining the shape of the molecules. He said that orbitals of similar energy, similar shape and orientation, these three are very important things: energy, shape and orientation. Energy, symmetry, orientation. If all the three are similar, then the orbitals may overlap, and when they overlap, bond will be formed, and the direction of the bond will be the same as the direction in which the orbitals overlap. Okay, so this is what Pauling said, that we can find out the bond direction and the shape by finding out the axis along which the bond is being established. Like this, we can have SS overlap, PS overlap, PP overlap. Blue portion is basically for positive sign of the wave function. Red is negative the negative sign. So S can overlap with S. S can also overlap with P. P can also overlap with P. P can also overlap with P like this, but there's a difference between these two overlap. This is the overlap along the internuclear axis. This is the overlap perpendicular to the internuclear axis. Similarly, this case. Now, this is a case of positive overlap. We can have SP, just like here, we can have SP here also, but the problem here is that the positive lobe is overlapping with the negative lobe. That is why we are calling it as a negative overlap. Positive should overlap with positive, negative should overlap with negative. If it is not so, it can be a case of negative overlap. Then we may have a case of zero overlap also, where we have a portion overlapping with the positive lobe, the other portion overlapping with the negative lobe. So both the two overlaps mutually cancel each other, giving us zero overlap. So on the basis of Pauling's theory, let us try to explain the shape of CH4 molecule. Okay, for CH4 molecule, the electronic configuration is 1s2, 2s2, 2p2. If I excite this, since I have to form 4 bonds, at least I should have 4 unpaired electrons. In order to do that, I excite the carbon atom 2s1, 2px1, py1 and 2pz1. Okay, so this is the excited electronic configuration for carbon. Apart from this, I have 4 hydrogen atoms. Each hydrogen atom having 1s1 electronic configuration. Okay, so let us see how the 4 bonds are being formed. One between this overlap, pz of carbon and 1s of hydrogen. Another bond may be formed between 2py of carbon and 1s of hydrogen. Then we can have overlap between 2px and 1s of hydrogen. And the 4th bond may be formed between 2s of carbon and 1s of hydrogen. Okay? As such, it seems to be okay that 4 bonds are being formed. But all the 4 bonds, are they equivalent? They are not. These 3 bonds are formed by PS overlap. This bond is formed by SS overlap. So, this bond ideally should be stronger than these 3 bonds. So, this bond length should be shorter than these 3 bond lengths, and hence there should be distortions in the geometry, plus there should be 2 sets of bond lengths which we should observe. One corresponding to this bond, another corresponding to these 3 bonds. But experimentally it has been found out that CH4 molecule is a perfect tetrahedral molecule. There is no distortion at all, and all the 4 CH bond lengths are equivalent. Whereas on this basis, we are not getting equivalent bond lengths, we are getting 3 bonds of one nature and 1 bond of another nature. But experiment shows that this is not the case. All the 4 bonds are equivalent to each other. That means there was some problem with the Pauling's way of explaining the shape. That needs to be modified, that needs to be rectified, and hence the concept of hybridization was introduced. Next. So, in order to explain the shape of the molecule, Pauling tried his best, but he was not able to explain mainly equivalent bond lengths. He was not able to explain according to the Pauling structure. I repeat, 3 bonds of one type, 1 bond will be shorter, like somewhat like this. We have this, 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 and 1 very small bond. And due to this small bond, the geometry will no longer be a perfect tetrahedra. The bond angles will be different. We'll have 2 sets of bond length, one corresponding to these bonds, another corresponding to this shorter bond. But experiment shows that all the 4 bond angles are equal, all the 4 bond lengths are equivalent, and hence Their modification was required in the Pauling's method, which was done via the introduction of hybridization. So, in hybridization, what happens is the orbitals of, again, similar symmetry, similar energy, they mix together to give us the hybrid orbitals, and the hybrid orbitals which are formed are of exactly the same symmetry and same energy. Moreover, the overlap of hybrid orbitals gives us a more directional and a stronger bond. Thus, the hybrid orbitals definitely are considered to be better in comparison to the overlap of pure orbitals. So, that is how the concept of hybridization was introduced. Let us study the ins and outs of hybridization. Okay. Please remember one thing, that hybridization never takes place in isolated atom. If I have carbon as such, it will never undergo hybridization. Hybridization only occurs when the atom is combining with other atoms. Say for example, carbon in CH4 will undergo hybridization. Carbon as such will remain as such, it will not show hybridization. Another very important point is that in the previous concepts, whether it was the Vesper concept or the Lewis concept, even in the valence bond theory, we said that the bond is formed when the two electrons are being shared, and the two electrons should be of opposite spin. Moreover, one atom should contribute one electron, the other should contribute the other. Was the condition. But for the formation of hybrid orbitals, there is no such condition. We can have empty orbitals participating in hybridization. We can have orbitals with one electrons also participating in hybridization. We have orbitals with even two electrons participating in hybridization. So, it is not necessary that orbital should have any electron. Orbital with 0, 1 or 2. All sorts of orbitals can participate in hybridization. And once the hybridization takes place, the hybrid orbitals are formed. Say for example, if two atomic orbitals mix together, 1s and 1p mix together, then since two atomic orbitals are mixing together, two hybrid orbitals will be formed. If three atomic orbitals are mixing together, 3 will be formed. If 4 are mixing together, 4 hybrid orbitals will be formed. And once these hybrid orbitals are formed, they are oriented in space again in order to have minimum repulsions. And the electrons are distributed in all these hybrid orbitals in accordance to the Pauli's exclusion principle and the Hund's rule. So, this is what I have shown, how sp hybrid orbital is formed. We have s orbital mixing with p orbital. Two such orbitals will be formed, hybrid orbital. This is one hybrid orbital, this is another hybrid orbital. Another thing which I would like to highlight here is that each hybrid orbital is having two lobes, this one and this one. This is the major lobe and this is the minor lobe. But whenever we show bonding, we just show the major lobe, because minor lobe is not important for us, so most of the time we ignore to show. Some of the books, they show the smaller lobe also, this is the minor lobe, but bonding takes place through the major lobe only. So, two hybrid orbitals are formed, they are oriented so as to have a minimum repulsion, and minimum repulsion is possible only when the these hybrid orbitals are at an angle of 180 degrees. If we are having three atomic orbitals mixing together like s and p, we have px, py mixing together, we will have three hybrid orbitals being formed. The three hybrid orbitals, they will be placed at an angle of 120 degrees. If we have three atomic orbitals, sp3 hybridization that we call is, the three hybrid orbitals again, they will be placed like the four hybrid orbital, I am sorry, will be placed in a tetrahedral manner at a bond angle of 109 degree 5 minutes. If we have five, just a minute, Okay, so when we talk about sp2 hybrid orbitals, where there were only 3 atomic orbitals that were participating, sp2 hybridization taking place. Now, once these hybrid orbitals are formed, these hybrid orbital, they may overlap with the atomic orbital of the other atom or with the hybrid orbital depending upon the molecule. I think I should give a halt here. More about hybridization we can talk in the next session, that is tomorrow, and we can have a quick round of question answer or any query you people have on any of the topics that we have discussed. Huh. Please pass it on.
What is the coordinate bond? Is it present N2O?
Is it present in
N2O?
N2O. Okay. Any other queries? Because N2O is a slightly complicated molecule. Yes, it is there.
Why lone pairs show greater repulsion than bond pairs?
Why?
Lone pairs.
Okay, the lone pair, as we have already discussed, the lone pair is basically under the control of only one atom, one nuclei, whereas the bonded pair is the pair of electron between two atoms. So, whenever the electron is under the control of two atoms, it will be restricted to a particular space, whereas when an electron is under the control of only one atom, it will expand in space and hence it will occupy more space. N2O, can you just try to write down the structure for N2O? N2O molecule. I think I have given you the structure for N2O. Okay, that means I think this question can be understood better when we talk about hybridization, because in case of hybridization I can show you how a coordinate bond is being formed. In case of N2O, that we have discussed, we have N, double bond O, double bond N, and how many lone pair were there on this nitrogen atom? 2 with a negative charge, this with a positive charge. Okay. Now, what happens in N2O is that this is a normal sigma bond, this is a normal pi bond. Okay. Now, this nitrogen atom, since this central nitrogen in our atom is having 5 valence electron, 1, 2, 3, 4 and 5 initially like this, normally what happens is that either it forms a coordinate with oxygen atom. Some of the books definitely show this structure also. But as I have just now said in the previous examples also, that instead of coordinate bond, the priority of oxygen is to form a double bond. If there is no scope of a double bond, then only it will form a coordinate bond. Moreover, some of the books shows the formation of the coordinate bond, but actually the structure is not this, it is this. Any other queries, please? Cl, ये मैंने दिया है ना, very smart indeed. Instead of getting it solved, asking me to solve it. Okay. Anyways, I've given you the tips for this also because this doesn't contain oxygen. So very simple to calculate. Central atom is chlorine. Number of valence electron on the central atom? 7 plus 1 for each of the surrounding atoms. That is 3. 10 electrons. That means 5 pairs. 5 pairs means geometry is trigonal bipyramidal. But out of the 5 pairs, only 3 are bonded. 2 lone pairs. So the lone pair should occupy equatorial position, and hence it is a T-shaped molecule. For ICl2 minus, ICl2 minus, again it will be 7 plus 2 plus 1, 10 electrons, 5 pairs, 2 bonded, 3 lone pair, trigonal bipyramidal geometry, but 3 lone pair, all these 3 lone pair occupying the equatorial position, the 2 axial positions occupied by chlorine, giving it a linear shape. If you just work it out, you get the answer. Any other query, question, doubts? Absolutely. Huh.
Why atoms form coordinate bonds if they are already stable?
Why?
Why atoms form coordinate bonds if they are already stable?
Okay. Now, why do atoms form coordinate bonds if they are already stable? Actually, when we talk about a molecule, in a molecule we have to look in the stability of each of the atoms. We can't say that the octet of one atom is satisfied, other is not. We can't leave it. We have to look into that all the atoms in a molecule, their octet is complete. So, in that situation, sometimes it happens that the atoms have to form a coordinate bond. If their octet is complete, but the octet of the other atom is not complete, in that situation, they have to be generous in forming the coordinate bond. We will discuss more example when we talk about hybridization, which will deal with this problem also.
What is odd electron molecule?
Odd electron molecule, if you add the total number of valence electron of all the atoms in a molecule, just add the total number of electron. If it is an even number, all the electrons are paired up, that means it is a normal molecule. If you have any odd electron left, then it will be an odd electron molecule. Say for example NO2. NO2 will be 5 plus 6 plus 6, that means 17 electrons. 17 cannot be divided by 2, that means it will have 8 electrons in form of pair and 1 single electron. That is what is meaning of odd electron. That is all. So thank you so much. We'll meet tomorrow then. Come prepared with the question which I have given.